that's my plan. I don't know if it's home or someone hid it in a class.
I could probably find an extra one. It's probably not the one that you want, though.
I'd rather take a look at home before I convert to a new planner, but if I can't find it, then I'm definitely getting a new one tomorrow, because that thing's like my life.
I know. I don't know if it's just me because I'm pregnant and my nose is on like super hyperdrive, but do we smell pizza or burgers or something in here?
Dog food to me.
It smells like dog food? Not really. Last period it smelled wonderful, like coming in the window. I don't know what it is. All right. Any homework questions? I've been asking a few days now, and no one has really said anything. So I'm assuming we're doing them. They're going well. Yes, ma'am. Number 12 from this past homework.
Yeah.
This one?
Yes.
Okay. Let's go ahead and tackle the derivative. First thing I would do is change the square root to a power. That way we could maybe use the power rule. So the square root of x is the same as x to what power? Yeah. Ooh, close. 1 over 2. 1/2. Okay? So, now that we have x's to powers and maybe a trig function or so, we could figure out the derivative. So when you look at your first term, we're going to use a power rule shortcut on that one. So that would be 3x to the negative 1/2. All right. And if we take a look at a derivative shortcut for the next term, what's the derivative of cosine? Negative sign. So we need negative 3 times the negative sign derivative. So that would change to a positive 3 sign. Okay. Typically, whenever you have that coefficient out front, like the negative 3, you can just keep it for the derivative. It ends up being multiplied together in the end. So you could leave your answer like that. Maybe you have a negative exponent and want to practice your rewriting skills. So you can move a negative exponent to the bottom, make it positive. Maybe you want to practice your addition skills for fractions. We could rewrite this another way. If this 3 sine of x is over 1, you'd have to multiply the top and bottom by an x to the 1/2 power, so that you have a common denominator. So this would change to a 3x to the 1/2 times sine of x. And that's all over the common denominator of 1/2. Okay, so 3 different derivatives all mean the same thing. They're just rewritten. Is that okay, Anastasia? Any of those are fine. Any other homework ones we want to check out? Going once. Going twice. Alrighty. Let's check out page 119. So, now that we're getting good with derivative shortcuts, we're going to try to relate those shortcuts back to, the graphical connections between an original function and a derivative. We've already discussed these. Okay, we're going to write them down again in a chart format so we're nice and organized. And we're going to go through different examples that would cause us to utilize these relationships. So, if I told you that the derivative is equal to 0 or is 0, what is that telling you about the original graph? Yeah. You have a max or min. We kind of explored this phrase yesterday. If you have a slope of 0, that's something else that's kind of considered or called a horizontal tangent. Remember that phrase yesterday? Towards the end we saw that. Horizontal tangent, flat line, slope of 0. okay? If I told you your derivative, aka slope, is greater than 0, aka positive, what does that tell you about the original function? The original graph, yeah.
It's increasing.
You are increasing. What if I told you your derivative, aka slope, is less than 0, meaning negative? What's your original function doing? Go ahead and pick a seat, Alex, okay? I heard it, I think. Decreasing, good. All right. Think about the next two. I'll be back in a second. All right, what if your first derivative changes from a positive value to a negative value? AKA you change from increasing to decreasing. What's your original function have? Or think about the graph. If you change from going up to going down, what are you creating? Yeah, a maximum. And what if your derivative or slope changes from negative to positive? Yeah, a minimum. Perfect. We remember those connections? We haven't lost them clearly. Okay, so we're going to use those today as justifications, okay, or proving some points to help us with some questions. Let's take a look at a graphical representation, though, towards the bottom here. We're going to say that this is an original function graph. Okay, something that we start with. And based off of this original function, we're going to draw a possible graph of what the derivative or slope looks like at different points. Okay, so I started to draw, or at least label, some key points that we're going to focus on. If you were to draw tangent lines at these spots, maybe draw in some little ones. Okay, only touching the f of x graph at those spots, just once. So what we're going to try to do is estimate, because this is just a picture after all, we're going to estimate the slopes or derivatives at these points and plot our results on this new graph. That would give us the graph of the derivative. So at this first spot right here, x value of 1, 2, 3, 4, 5, 6, negative 7, what does the slope of your tangent line kind of look like it is? If you were to do rise over run to get another good point along that tangent line, can we estimate the slope at that point? Does it look like roughly 2? Maybe? Okay, so at the x location of negative 7, our slope or derivative is 2. We're going to plot that idea on our derivative graph. So at the x location of negative 7, we said the slope or derivative was 2. We're going to plot that ordered pair, that relationship. Okay, we're going to keep going through all these different points. That way we can at least connect the dots and see what our derivative graph looks like. All right, so our next location of negative 6, can we estimate roughly what that slope would be? One, maybe? Okay. So at the x location of negative 6, our slope was 1. Our next location, 1, 2, 3, is negative 4. What's our slope at that maximum? 0, right? So at negative 4, slope of 0, we're on the x-axis. Our next point is at the x value of negative 2. What does the slope look like at that spot, roughly? Maybe -1? About? Let's see, our next dot's at -1. The slope at that spot. About -2? Okay. Alright, looks like our next spot at 1 is a minimum. We know the derivative or slope there is going to be 0. Okay, horizontal tangent line. Our next location's at 3. That slope, perhaps, looks like about 2. Let's see, our next location, 1, 2, 3, 4, 5, we have a maximum. So we know that's going to be a slope of 0, horizontal tangent. And our last one at 7, maybe -3, about. Can we get those points, roughly? Estimations? Okay, so what we're going to do is kind of play connect the dots. You're not going to go through necessarily all the dots, because wouldn't that really be a weird shape, first of all, because this doesn't really look like a smooth curve type location in here. Can you pinpoint which of these dots we plotted are exact? We know for sure those points are there. Therefore, the graph we draw must go through those locations. Yeah. The zeros, the x-intercepts, right? Because those are where we had maxes or mins. We know for sure that those were values or slopes of 0. So the graph you draw has to go through those x-intercepts, but the other points you drew are just guiding points. Okay, those were estimations. We might be a little off. We're not quite sure. So if we were to draw a graph exactly going through the x-intercepts and using the other ones as guides, maybe it'll look something like that. Okay, this is a rough graph, just a possible graph. We were estimating some values. Okay, let's see if this graph actually makes sense. If you take a look at the original function graph, can you describe, based off of its shape, what power or degree it would have? This polynomial roller coaster type graph kind of looks like a W. Do we know what name has a W-shaped graph to it? Yeah? It's a quartic, yep. Okay, so what should have we anticipated as a derivative graph? What does this one look like? Cubic, right? The derivative is always one less power, one less degree than the original. Doesn't that make sense off the power rule? Don't you bring down the power and then subtract 1 from the exponent? You lose something from the power. Okay, so makes sense graphically. Perfect. Alright, so using these connections from the top, okay, we specifically looked at maxes or mins to help us draw this graph, those high points and low points to get those slopes of 0. Let's start to bring in some ideas of increasing and decreasing. Okay, so we'll look at these on the back. So I'm pretty sure this is the same graph we just did. We're just going to answer some different questions about it. So this is the graph of the original function, okay, f of x. Answer the following questions about the derivative, or about the slope of this graph. So our first one is to approximate the value of the slope at 4. 1, 2, 3, 4. Okay, now if you were to go to the x location of 4 and find the spot on your graph, we're somewhere right there. Okay. Now, we talked about two different ways we can approximate the derivative. The way we just did on the last example was to draw a tangent line and try to figure out rise over run. Okay, graphically speaking, you could try that. But there was a second way that we discussed estimating the derivative. I'm curious if we remember that method. Yeah.
Doing the finding the slope between the 2 points.
Okay, so we're going to use a slope of a secant line to help us estimate the slope of a tangent. So if this is the tangent point, we want to pick a point we know before it and a point we know after it. So that would kind of be these 2 points here. And notice how if you found the slope between those 2 points, wouldn't the blue line and the red line have roughly the same slope? Don't they kind of look parallel, right? Okay, so we have options here. Do we want to try to estimate rise over run of the red line? Or do you want to simply find the slope of the 2 points on the blue line? Do we have a preference? Either ones are going to give us good estimations. Which one do you guys want to do? You want to use the 2 points? I think that might be a little bit more accurate because at least we know that those 2 points are there. Okay, so let's take a look at our 2 points. We have the ordered pair 3, -1. And the other one, 1, 2, 3, 5, 4. Okay, so maybe we'll just say, so if you guys go ahead and reference your notes later, the slope at 4 is roughly the slope of the secant line through, okay, I'm using my texting language right there, through those 2 points. So let's go ahead and estimate what the slope is specifically at 4. So slope between 2 points, difference of y's over difference of x's. We can have -1 minus 4, and then 3 minus 5. It doesn't matter the order as long as you keep them organized. So -5 over -2, which would give us 5/2. Okay, maybe we'll check to see if this actually makes sense. If we tried rise over run, estimation-wise, this point we have to go up 5, 1, 2, 3, 4, 5 over 2. So it kind of looks like we would have gotten that, right? If we estimated tangent doing rise over run, pretty close. Okay, but either way it would give us a pretty close approximation. All right, let's check out 2. At what values of x is the derivative or slope 0? And then we're going to justify our answers. Okay, so go ahead and take a look at the original graph. Where would you have a slope of 0 if you were to draw in your tangent lines? Where would they be flat? Can we pick apart those x locations? What do you think, Braden?
-4, -1, 5.
-4, 1, and 5. Okay? So if I were to draw in tangent lines at those spots, notice how they would be flat. Okay? Justify your answer. Why'd you pick those? Because?
They're all relative masses of mass.
Alright, because f of x has a max or min at these locations. Alright, so I want to show you guys something real quick here. This chart we filled out on the front, okay? This is kind of your go-to to help you with your justifications. If you figure out a slope of 0, this is why. Okay, you can simply give that as a justification. Whereas we're eventually going to get to some analyses of this or this value, which then we would use this as our justification. Okay, but if you know this, this is your reason why. Okay, if you know this, this is your reason why. Okay, justification. So it's nice organized in a chart format. Okay, let's go ahead here. On what open intervals is the slope less than 0, aka negative? So if you were to draw in your tangent lines, okay, maybe we'll do that quickly. If you were to draw in some tangent lines, which one of those would have negative values? Can you give me an interval, like a beginning and ending point? What do you think, Joseph?
Negative 4 to 1.
-4 to 1, okay.
And 5 to
Because
f of x
is decreasing. Okay, notice again, based off of our chart, I'll bring that up in a second, the slope we said was less than 0 because the f of x graph was decreasing. Okay, let's switch it up. On which intervals is the slope positive? So all those tangent lines, where do they have positive slopes? Can we give some intervals? Let's see, I'll do the first one. Negative infinity to -4. Can we find another one? Good, Anastasia? 1 to 5. Because? Yeah. F of x is increasing. If you're increasing, your slope is positive, aka your derivative. Good. All right. Number 5. At what values of x does the graph of the derivative go from being below the x-axis to above the x-axis? Oh boy. Okay. So they're asking us at which values does the graph of the derivative, okay? This is not based off the information at the top, right? Because this is the graph of the original. So they're being a little tricky here. At what values does the graph of the derivative go from being below the x-axis to above the x-axis? If the derivative graph is below the x-axis, is it positive or negative values? Below? aka negative, okay? So the derivative is going from a negative value to above the x-axis, meaning a positive value. So if your derivative changes from negative to positive, what should we try, or what should we be trying to analyze on this graph up here? What should we be looking for? If your slope goes from negative to positive. Yeah? A minimum. All right, so notice how that minimum, before that point, the slope was negative. After that point, the slope was positive. So it says at which x values? So that would be at the x value of 1. All right, justify your answer. X value of 1 because... What do you want to say? Because there was a minimum, maybe? There is a minimum on the f of x graph. You could say because f of x changes decreasing to increasing. We said that was another way to signify a minimum was happening. Okay, lots of different reasons. Okay, I'm not saying one is more clear cut than the other. You just have to somehow explain your reasoning. Are we doing okay so far? Not too fast? My whole Goldilocks thing just right? Alright. At which x values does the graph of the derivative go from being above the x-axis to below the x-axis? So above the x-axis means we have a positive slope. Below the x-axis means we go to a negative slope. So take a look at the graph at the top. Where do you go from having a positive slope to a negative slope? Yeah.
-4 and 5.
-4 and 5 because
There's a max f of x.
there is a maximum on the f of x graph. Okay, one way you could phrase it, you could say because the f of x graph changes increasing to decreasing. Okay, that's the whole idea of positive slope to negative slope, increasing going up, decreasing going down. Okay, lots of different ways to phrase it. Alright, so far so good. Let's go ahead and switch it up. And this time, thanks Dan. Okay, this time we have the graph of a derivative. Alright, so a different beginning graph. So we're going to have to analyze this one a little bit differently than we did the other one. Not right now. Okay, I need you to come in before. And did you ask me before if you could take it? Okay, not right now. Okay? Alright, so pictured below is the graph of the derivative, specifically from -3 to 4. We're going to try to answer some of these questions. On which open intervals is the graph of the original function? So we got to make that connection between derivative and original function increasing. So if you want the original function to be increasing, what does your derivative have to be? What does your slope have to be? Yeah. Greater than 0, aka positive. Okay, so where is this derivative graph, aka slope graph, positive? Can you find the interval? Beginning point, ending point. Yeah.
0 to 2?
That's where this graph is increasing, but this graph is negative right here. It's below the x-axis. This is when it gets confusing. -3 to -2. Okay? The slope graph is positive right here. You are above the x-axis. Bless you. Right? So that's our interval because the derivative is positive. This is the graph of the derivative, so we need this graph to be positive, aka above the x-axis. Good. On which open intervals is the graph of the original function decreasing? So if you want your original function to decrease, what does your slope have to be? Yeah. Negative below 0. Okay, so if this is the graph of slope, where is this graph negative, aka below 0? Can you give me those intervals? Yeah. -2 to 2. Ooh. And 2 to 4. Why did you not include 2? That's good.
Because it's a 0 slope, so it'd be a max at 1.
Perfect. Alright, so at this spot, okay, the derivative is 0. Notice how 0 is not a negative number. Okay, we needed it to be negative so our graph was decreasing. So you're just wanting the points below the x-axis, not on the x-axis. That's a little tricky there. So these are the intervals where the graph is below the x-axis, and we'll say because the derivative is negative. All right. At what values of x does the original function have a horizontal tangent? Horizontal tangent means what? Yeah. Max or min, aka slope of 0. Okay, you would draw a horizontal line. So, if this is the graph of slope, where does this graph have a value of 0? Yeah. Negative 2 and 2. We are on a roll. Okay? Justify your answer because the slope is 0 at those spots. Alright, number 4. At what values of x does the graph of f of x, the original function, have a maximum? So we said negative 2 and 2 were the possible locations of maxes or mins. Can we figure out which one's a max maybe? Yeah.
Negative 2 because derivative is positive negative.
There we go. Negative 2 because the derivative or slope goes from a positive value above the x-axis to a negative value below the x-axis. So we'll say because the derivative or slope changes positive to negative. Let's switch it up. At which values on the graph of the original function do we have a minimum? What do you think, Braden?
2.
Why?
Because the derivative changes from negative to positive.
Does it? Before it, you're negative.
Nope.
After it, you're still negative, right?
Yeah.
All right. Dang it, right? We said these were our only options, right, for maxes or mins, because that's where we had those horizontal tangents. So this one was clearly a maximum. This one, though, if there's no change, you're not going up to down or down to up. So this is actually not a max or a min. So we'll say none because we don't have any other option to choose here. None because there is no location where the derivative or f prime changes negative to positive. Okay? So this is what's a little weird about this location here at 2. If you were to think about a graph that was decreasing initially, then has a slope of 0, is flat, and then continues to decrease after that, can you imagine what that would look like? Yeah?
It be going down and come to like a horizontal and then go vertical.
So on the original graph, okay, f of x, this is probably what's happening. You're decreasing, you level, and then you decrease again. Can you visualize that? We're going down, we level off, okay, a slope of 0, and then we continue to decrease afterwards. Okay, so that's kind of what's happening here. So just because we have a slope of 0, that's a possible max or min. Not necessarily it's definitely going to be one, because you could have kind of a level spot. Maybe we'll make note of that here. Okay, we have some type of level location. No max or min. All right, let's go ahead and check out 6. What is the slope of the tangent line to the graph of f of x at the x location of 0? When I say slope, you think tangent, aka derivative, okay? So if we want the slope of the tangent line at 0, we want the derivative at 0. If you were to plug in 0 into the derivative graph in this case, because we have a graphical picture, what would you get out? Can you tell based off the top graph? What's the point value you would get out? -2. Okay? So we would say the slope of the tangent line at x equals 0 is -2. Because we'll use that mathematical notation as our reasoning. Okay? The slope, aka derivative at 0, based off the graph, was -2. Alright, let's amp it up a bit. What is the slope of the normal line to the original graph at x equals 4? Justify your reasoning. How is normal related to tangent? What's the connection between the two? Yeah, they're perpendicular. Alright, so we got to figure out what's the slope of the tangent line at 4, aka the derivative at 4. Can you find that based off the graph at the top? That's the graph of the derivative. That's the graph of slope. So we're going to plug in 4 into that graph, and what do we get out? -2. So if that's the tangent slope, what would our normal slope be? If they're perpendicular? Yeah, 1/2. We need the opposite reciprocal. So we'll say the slope of the normal line is 1/2 because the normal line is perpendicular to the tangent line. And we found the tangent line to have a slope of -2. Are we okay with these connections? Making sense? Okay, it all depends on what you're given. Are you given the graph of the original, or are you given the graph of the derivative? You got to analyze them two different ways. Okay, for the derivative, we're mostly concerned with above the x-axis or below the x-axis. For the original function, we're concerned with, are we increasing or are we decreasing? Okay, two different analyses, so you have to be aware of what you're actually working with. All right, we still have a little bit of time left, but for tomorrow, we're going to take a look at how can we continue to figure out where a graph is increasing or decreasing, where it has a slope of 0 or a negative slope, those kind of concepts. We're going to do them by hand, though, no graph. Okay, analytically means by hand. So we're going to get into the good algebra work for these cases. Okay, but we'll save that for tomorrow.
How does that change the x coordinate? Like, are you adding something to the x coordinate? Are you subtracting something from the x coordinate? I'm wondering what those are. Just not. So this is acting on that coordinate, whereas he's at one.